All right, hello everyone. In this demonstration, I want to show you how you can figure out the uncertainty in a calculation. Given that you have some measurements you've made and you want to use those measurements in an equation to calculate something else, what's the uncertainty in that something else? So I'm going to use an example. I'm actually going to use an example slightly more complicated than what you encountered in your labs, but it encompasses a lot of the ideas that you're learning. So here we go. Let's start here. Fire up the pen. Now, suppose we have some mathematical, physical relationship that says this, that n is equal to 4 multiplied by x plus y multiplied by z squared. And suppose that x, y, and z are measurements. So that x you determined was 2.0 plus or minus 0.1. We won't put any units in this stuff today. Suppose y is 5.3 plus or minus 0.2, and that z is equal to 4.1 plus or minus 0.3. Now I want to point out with these numbers over here, these are measurements. Maybe they're times, maybe they're forces. Whatever they are, you have measured them with some device. And you've recorded some uncertainty with those values. And so what you're saying, if we look at x, you're saying that you're fairly confident that x is between 1.9 and 2.1. You're fairly confident that y is between 5.1 and 5.5. Now, these uncertainties, you had to estimate. And remember, this is covered in the handout for the sort of uncertainty in measurement, that there's three things that come into play. There's the thing doing the measuring, there's yourself, and the thing that you're measuring. And all of those you have to bring into play when you're figuring out what this uncertainty is. There's no formula for that. You have to make those decisions as the experimenter. You have to think about the experiment you're doing and how well you know your measurements. Now, having said that, suppose again we have this relationship over here, and I've totally made this up, but it's telling you that this new quantity n is equal to 4 times x plus y all multiplied by z squared. And the challenge becomes, what's the uncertainty in n? That's what I mean by this squiggle. Uncertainty in n. What is it? And at this stage, we don't have to do any more estimating. The uncertainty in n is totally determined by the uncertainties in x, y, and z. And how do you figure that out? Well, this looks mildly complicated, this equation here, but you can kind of break it down. Notice for a second, there's sort of three distinct regions. There's the 4, and then there's the thing in the bracket, and there's z squared. I can write that as n is equal to, if I want to, I could say a times b times c, where I'm calling that a. I'm going to call what's in the bracket b, and I'm going to call this what's squared c. And notice that's three numbers multiplied together. Now, if you check with the lab for this week, or maybe depending on when you're listening to this, maybe it was last week, the rule for multiplication is that the uncertainty in n, and this right here is called an absolute error, divided by n is equal to the uncertainty in a divided by a plus the uncertainty in b divided by b, make that a little bit better, plus the uncertainty in c divided by c. Again, that squiggle, it's actually the Greek symbol for delta, and I'm using it for the uncertainty n. But you notice you just got to add them along. If this was A times B times C times D, I would just add on another plus uncertainty in D divided by D. Now this is what we're looking for. And we have to start wondering what are some of the things that we know. Well, one thing, when you've written it like this, you can now write it and get rid of the A, B, and C stuff. If you look at it, what did I call A? Well, it's actually 4. So it's the uncertainty in 4 divided by 4 plus the uncertainty in B. Well, B is whatever's in the bracket, x plus y, divided by x plus y, and then plus the uncertainty in C. Well, that's the uncertainty in z squared divided by z squared. So there you go. So how you can string those guys along. Now, if you look up here, we have x, y, and z and uncertainty in those values, and down here we have x's and y's and z's, but they're squared and they're added together. So what do we do with that stuff? Well, let me write it on a new page. And again, let me just write down our values here really quickly again. And y 5.3 plus or minus 0.2. And here's our z plus or minus 0.3. And notice where we left off, we had uncertainty in n over n equals uncertainty in 4 over 4 plus the uncertainty in x plus y over x plus y plus the uncertainty in z squared over z squared. And again, it looks a little bit complicated. Now, I'm just going to use the rules. I'm not going to take the time out right here to explain where they came about. Most of them are talked about in the lab on measurement in physics. So one thing, let's start here. This one here, this is the uncertainty in 4 over 4. Well, that actually evaluates to 0 simply because 4 is a constant and there's no uncertainty in that. So it's 0 divided by 4. Then you come over here, and now we have, what's the uncertainty in x plus y? Well, that's an addition, and the rule is for addition, you just add the uncertainties. So it's actually uncertainty in x plus the uncertainty in y divided by x plus y. So that's kind of how you do that. And then for this guy here, when you have a quantity squared, what you do is you actually bring down the power. In this case, it's raised to 2, and it becomes the uncertainty in z over z. Notice it's not divided by z squared. If you have this part right here, we have the uncertainty. You want to know what's the uncertainty in z squared divided by z squared. It's just 2, this power right here, multiplied by the straight uncertainty in z over z. You probably wonder, where did that come from? If the 2 up here happened to be a 4, then it would actually be 4 that would appear in there. Now, notice we can start to evaluate a few things here. And I want to point out this quantity here, this ratio of the uncertainty divided by the quantity is actually called a relative error, whereas just the top part is actually just called the absolute error. But notice now we know a lot of things here. There's the uncertainty in z, and there's the actual z value. Same with y and x. So we can start to do a few things in here. We can say, okay, the uncertainty in n over n is equal to 0. We don't have to keep carrying that around. So the uncertainty in x is 0.1 plus the uncertainty in y is 0.2, all divided by x plus y. X is 2, y is 5.3, so it looks like it's going to be 7.3, and it's going to be plus 2 times the uncertainty in z, which is 0.3, divided by z, which is 4.1. And we can take another step here. If I've done my math right, this guy here amounts to 0.041, and the other one, this guy, amounts to 0.146, which comes together to give us 0.187. So look what we have. And this is an important step, not that the other ones weren't important. 0.187. So we have that the uncertainty in n divided by n is equal to 0.187. Now this is interesting because we're actually just a small step away from finding a percent error. If you were to multiply this by 100 and multiply this by 100, kind of look what you have. You have about 18.7%. This is telling you that the uncertainty in n over n is 18.7, which is, you know, if you got a test result and you got 2 out of 10, that's 20%. Well, here's the case for saying that the uncertainty is 18.7% as big as the actual value. So this is essentially the plus or minus uncertainty for that quantity. Now we can find the absolute error now. So let's go to another page. Let me write this down again. Uncertainty in n over n, and we'll write it without it written in percent form, is this. Now I haven't been dealing with significant digits too much at this stage. I'm going to tidy it up in a second. Now one thing we want to do is if we can calculate this, n, and remember n is just 4 times x plus y multiplied by z squared. So that's going to be 4 multiplied by 2.0 plus 5.3 multiplied by 4.1 squared. So notice I'm figuring out n. I don't put any of the plus minus stuff. I'm finding the best value of n based on my best values of x, y, and z. And again, if I did things right on my calculator, I get about this. And again, I'm writing down a lot of extra digits. I'm going to tidy it up in a second, but I get 490.852. So we can write that the uncertainty in n over 490.852 is equal to 0.87. So I can solve for the uncertainty in n simply by doing a little bit of mathematics. 490.852, and that gives us something about, I ended up writing this down, 78. So 91.78. Now, one thing I want to say about this thing here, this uncertainty value, this should only ever have 1 or 2 digits. I should say significant digits. So right away I want to think about writing that as maybe at best 92. So then when I look back and I look at my raw number, since this is 92, notice that the value for n, which I got at 490.852, A lot of these digits back here, the 8 and the 5 and the 2, they don't make a lot of sense. They don't carry any additional information because the uncertainty is so big, the order of close to 100. It doesn't make a lot of sense to try to pin down the actual number to 1,000 or 100. So I look at that and I say that, you know, a respectable answer is n is equal to 490, we'll say 1, plus or minus 92. I would consider that acceptable. Now, given that x and y and z had two significant digits, you could also use power notation to write this as, say, this. N equals 4.9 plus or minus 0.9 times 10 to the 2. And notice this guy here has one digit in him, which is fine. This has 2, the actual n value. And you multiply it all by 100, you've got the right size. But I would accept both of those. You know, you could argue that this one here is carrying one too many, but only just by a bit. You definitely don't want any more than that. Again, this is an important rule. Only one or two digits in an uncertainty. So anyhow, that's a quick run through. So if you go through that a couple of times, hopefully that'll make a little bit of sense. In the lab, or maybe you've already done the lab, or you're working on it now, you'll have done a few examples that are a little bit simpler than that. All right, I think we'll let you guys go. This is getting pretty long. I'll keep that stuff, and I will see you guys later.